Okay, so now in this example, we're dealing with the projection pi, right, that we've seen before. Now, before we get into this, just remember when we talk about eigenvalues and eigenvectors, I think it's useful to understand that eigen comes from the German word for characteristic of or peculiar to. So some authors will call eigenvectors, eigenvalues, characteristic values, and characteristic vectors. Nobody ever calls it peculiar vectors, but you will see authors that will use the word characteristic instead of eigen. So now, in this example here, this projection map pi has an eigenvalue of 1 associated with any eigenvector xy 0. Okay, so that's one thing to understand. Where x and y are scalars that are not both 0. Okay, that's, again, just keep in mind, x and y cannot be both 0. Now, in contrast, a number that is not an eigenvalue of this map is 2, since assuming that pi doubles a vector leads to the three equations, x equals 2x, y equals 2y, and 0 equals 2z, right? And obviously, this does not lead to a doubling of the vector for any non-zero vector xy0. Okay, now note that the definition requires that the eigenvector be non-zero. Now some authors allow 0 vectors as an eigenvector for lambda as long as there are also non-zero vectors associated with lambda. The key point is to disallow the trivial case where lambda is such that t of vector v equals lambda times vector v for only the single vector where v is the 0 vector. Okay. Also note that the eigenvalue lambda could be 0. The issue is whether whether this vector is equal to 0 vector. Okay, that's it.